You're listening to KTAL LP FM in Las Cruces, New Mexico, 101.5.
Not hearing you here.
We're also streamed live on lccommunityradio.org or radio KTAL, QUETAL.org. I'm your host, Vince Gucic, for this segment, Science. Let's take a look. We'll cover all kinds of areas of science. And with me in the studio today are John Nelson, engineer. He's been here on a show back on December 26th. And Craig Ricketts, who's new to the whole thing. They'll jump in as they see fit. Meanwhile, I'm going to start out with a little segment correcting some misconceptions. There's a book called, let's see, what is it? Dumb History, written by a fellow, Joey Green, who does lots of things. Anyway, he wrote a whole series about, well, history, but a lot of it was about science. And I read the book. I said, oh, gee, there's a lot of misconceptions here. So let me address one of them. And I have to admit, I wrote to Joey Green, and he was extremely gracious about what I offered. So I like Joey. He had a segment on page 194, underestimating the gravity of the situation. And his take on it was when Einstein developed general relativity, that completely overthrew Newtonian mechanics and Newton's idea of gravity as a central force acting at a distance. So what I said is that led us to understand, Newton's theory that is, led us to understand the motion of the planets and so much more. And it's a fantastically accurate approximation to the relativistic view. So Einstein didn't really disprove the theory. What he did is he extended it in a whole new framework and gave us things that are even more accurate. So I can hear you guys. So unless you're traveling a few thousand times the speed of your car, you're not going to have to worry about it. Now, there is a case in everyday life where relativity came into play, and that's in the GPS system that gives us our location. The engineers who put up the satellites said, well, I'm not sure about this relativistic correction, but if you insist, we will, put in a little switch where we can engage the relativistic correction if necessary. So first, they turn on the GPS system without the switch, and the apparent position of points on the surface of the Earth drifted by 11 kilometers every day, because clocks run differently in space and also at different gravitational fields. So, okay, it's on now, and that's the short story of how theories extend each other, and that's the way that science works. The next thing I'd like to go into is about this planet, exoplanet, meaning outside our solar system, Proxima Centauri b. That was discovered last year. Can't really hear all that. Yeah, by the European Southern Observatory telescope in northern Chile. And the way they detected this planet, which is, by the way, at the location of our nearest star, was by the wobble of the apparent position of the star along our direction of view. Now, there's a lot to say about that, but it's not what I want to do here. That star and its planet are 4.25 light years away, an extreme distance for any probe. There are people who are talking about going there, not personally, but with tiny little microcircuits propelled to nearly the speed of light, ultimately, with laser beams. Even Stephen Hawking bought into this. I don't think it can possibly work. Once you get there, what kind of a signal could you possibly send back? But that's, again, not the whole deal. The interest of many people in exoplanets is, well, first of all, to see how solar systems form around other stars, and then to look for life. I think some of the idea about looking for life is to get popular support rather than thinking that they'll ever find it. But there was a claim that maybe this planet could support life. Now, Proxima Centauri b, there's 3 stars out there, that's why it's B, is a kind of a weird star by our standards. It's cool, so it's only half the absolute temperature of the sun. So if you're used to English units, live in the United States, Liberia, or Myanmar, our sun is at 10,000 Fahrenheit, or if you live in the rest of the world or are a scientist, it's 6,000 Kelvin, or around 55, somewhere in between 5,500 and 6,000. And anyway, the other thing is it's small. Its diameter is only 1/6 that of the sun. Now, the planet is very close to the star because otherwise it would not be of interest. It has to be close enough so that even with a pretty weakly radiating star, it receives enough starlight to stay warm. Okay. Now, we can calculate how much energy gets to the surface of that planet thanks to the discoveries of physicists like Max Planck, Albert Einstein, Joseph Stefan, Ludwig Boltzmann, and others. So we can consider the star as a black body, a really good approximation. Doesn't mean it's not visible. All it means is it radiates effectively at all different wavelengths, colors, etc. Just as a perfect absorber would absorb all those wavelengths. So that's a historic thing about calling it a black body. Now, the total amount of radiation per unit of surface area of that star, well, actually anything, is proportional to the 4th power of the absolute temperature. If you're not used to absolute temperature, you take it from absolute 0. For the metric system, that's in Kelvin, and that's 273.16 degrees below 0 Celsius. And if you do use English units, I forget, it's like 459.6 degrees below 0 Fahrenheit. Now, if that star has that lower temperature, and it's a little bit more than half the absolute temperature of our sun, it's only putting out about 7.5% as much power per unit area as our sun does. So how does the planet get warm enough? Well, it's close. And it turns out that, I'm looking for the figure here, but it's close enough that it gets about 88% as much energy per unit area as we do on the Earth, at least for the part that's facing that star. Okay. Another thing that you have to think of is it's not just keeping warm. Anything that's living on the planet has to make use of what we call high-quality energy, lots of free energy. That means particles of light, photons of the right wavelength, short enough that they contain a lot of energy to break chemical bonds and drive the reactions of life in photosynthesis as the basis of life anywhere. So if you take the cutoff as a wavelength of 850 nanometers, and just to give you scale, 700 nanometers, shorter wavelength, a little more energy, is where we start being able to see things with our vision. And we cut off at around 400 nanometers, shorter wavelength, higher energy, very blue. So I did a calculation of how much energy is available in that weaker spectrum for any bacteria that might be on that planet. And they get about 32% as much energy per area as all of us on Earth. That's probably enough for an ecosystem, but there's a little problem here. Basically, if a planet is that close to a star, it is likely to be what we call tidally locked, that the gravity is fairly intense. It distorts the planet enough that the gravity has sort of a handle to grab onto, which means that it doesn't rotate. And that's what happened to our moon. Our moon is close enough to us, even though it's still moving out slowly, that it's tidally locked. That's why we never see the dark side of the moon. So this planet is always facing with one particular aspect to that star. So here's a problem, just as it is on the moon. The side that's always facing that way is very hot. The part that's facing away is very cold, basically about the temperature of interstellar space, about 4 Kelvin, like minus 269 degrees Celsius. So even though the average temperature on the planet might be about right, the livable area with moderate temperatures is a pretty small slice. I actually calculated what that would be, and it's a small range of angles away from looking right at the star. You might say, okay, there's some habitable zone. Another problem, if there is a very cold spot on that planet, the atmosphere will slowly, actually pretty fast by geological time, condense on that side. There's no atmosphere left anywhere else. So astronomers now think that it is pretty clearly tidally locked. So that's the end of the idea that there could be anything living on that planet. I can go into some more detail, but let me ask John and Craig if they have any comments on this. What do you think?
We know, Vince, a lot of people are really excited about the idea there being life outside in the solar system. And so, you take a very scientific approach, kind of a bummer for people who are really hoping that there's something going to happen. And of course, we've seen a lot of activity of listening for
the SETI program?
The SETI program. But I can hear what you're saying, and it probably applies more when you even look further out into space. So maybe there's not much hope there.
Yeah. My total analysis, and you've got a copy of what I wrote, says it'd be really, really rare for finding life. So don't expect it to be anywhere near us if it does exist. And there's all sorts of cool things, but what a planet has to look like to be habitable. But let's go back to something Stephen Hawking said. Stephen Hawking likes this idea of sending probes out there to Proxima Centauri b. He doesn't expect to see life. And he once made a comment, I'm pretty sure I'm attributing it right. He says, shut it down, because if they're so powerful they can contact us, we're going to be either food or pets for them. He didn't phrase it that way, but that's a pretty close approximation. I'm going to make a short station break here, and then we'll be back with all kinds of more science. Thanks for listening. Remember, it's KTAL LP FM in Las Cruces, New Mexico.